Hello, everyone. This is Thomas Boyd from MongoDB. Thanks for joining today. Happy to have all of you here. It's a little bit after 9 o'clock Pacific, which is where I'm located, so let's go ahead and get started. So the topic today is achieving scale with MongoDB, and as I mentioned, I'm Thomas Boyd. I'm a Director of Solutions Architecture here at MongoDB, and we're going to go over a high-level discussion of some of the tips and tricks for running large-scale systems with MongoDB. This is a very, very big topic, so we'll kind of be touching the surface of things like horizontal scaling and scaling through making changes to your hardware. There are more detailed discussions on many of these topics. So I wanted to start this talk with this slide. So that bottom line there in black is actually from a benchmark that was published several years ago, an external benchmark that was showing the number of operations per second that were happening on a MongoDB cluster as they used our partitioning strategy, which is called sharding, to add more capacity. So the story they were telling was, well, when we started with one node, we got roughly 5,000 operations per second. This was a mixed read-write workload. We added another node, and the overall throughput for the cluster actually went down. And as we bumped up to 4 and 8 nodes, the claim from the benchmark was that they really didn't see a significant improvement in throughput. And I'm here to tell you it's absolutely possible to do this with a MongoDB cluster. If you don't understand some of the fundamentals of how to scale your system, if you don't understand the details of choosing a good shard key if you're going down this approach of partitioning your cluster, or if you don't understand where the bottleneck is, simply throwing more machines at the problem won't solve it. That said, the green line represents what you can get with a well-thought-out scaling strategy, where you've made the right decisions and you understand some of the internals that we're going to talk about today. So a high-level agenda here. We're really going to start with basic optimization tips. And one of the themes that you're going to hear is, if you don't get these basics correct, then the other ways to scale your system are not going to work real well. And so, really there's been 3 fundamentals that I've always stressed for optimization. It's around schema design and indexing, and then doing proper monitoring of your system, understanding what the baseline performance is. I did want to add in a 4th topic, so that the WiredTiger storage engine was introduced a couple of months ago. And for particular kinds of bottlenecks, it's going to be a great solution for you guys to get more raw performance, more scale out of your MongoDB system. Then we'll talk a little bit about vertical scaling, taking your individual box and making it larger or more powerful by adding either memory or I/O bandwidth or CPU. Then we'll talk about the partitioning strategy in the horizontal scaling section. And we'll close with a brief talk about scaling challenges that you may have in your operations team. So, the human element of running large systems is often overlooked and is critically important. So we'll talk a little bit about that. So schema design. If you've seen MongoDB already, then you're familiar with the document model. And this is really one of the main reasons why MongoDB adoption has gone through the roof and why it's so popular with the development organizations. This document model is really easy to work with. It matches the way your application wants to interact with your application data. So whether you're programming in Java and you have objects, or in Python, or in Ruby with associative arrays, or hash maps, it's a great match with the way your applications want to interact with the database. It's very flexible, so you can add new fields into these documents quite easily without having to go through a separate schema design step. And you get a lot of inherent high performance out of this model. And the reason for that is, when you have a rich document that has encapsulated all the information that your application wants, it's a relatively simple step for the MongoDB database to retrieve this document, either based on a primary key lookup or on some secondary indexes that you've created, and present it to your application, and then your application can act on it the way it needs to. a relational database might have broken up this kind of information in a bunch of different places with a master table and a detail table. And that means that inherently that relational database has a fair amount of work to do if it needs to reassemble that whole object. There is, a little more complexity in some ways that's introduced when you have this document model, in that schema design is radically different than the way you used to do it in relational databases, if that's the background you've come from. So in relational databases, it was possible to have a look at the domain, the entities that you were trying to model, and basically reduce that to third normal form and know that you had the correct representation just by looking at your data. And then the reality is that a lot of relational systems would have to do some optimization from there. They might do some roll-ups, or they might do a few things that break third normal form just to get better performance. In MongoDB, you're really denormalizing the data, and you're going to create this potentially complex schema that is really driven by the way you expect your application to interact with the data. So, the classic example is if I were modeling sales orders, I would have the sales order header information together with the sales order line information all in one document, so I could quickly retrieve that information. This means that the queries that you write are quite simple, and there's less work for our database to do. So, there are a couple classic mistakes we see with schema design in MongoDB, and the number one most common mistake is for people to take a relational model that has master tables or header tables and detail tables and just create MongoDB collections that are an exact match of those original relational database tables, as opposed to combining them together into a rich document. So, we often get called in to do performance tuning or deal with scalability issues, and we immediately find issues in this schema design that are kind of the underlying root problems. Less often we see an error where people tend to get a little bit overboard with very rich documents. You get large documents with arrays that have tens of thousands of elements in them, or very, very deep nesting inside the sub-documents that you can create in these MongoDB documents. And that has its own set of challenges. So it's not as if you're gonna munge everything together into one single document. And I always fall back on the recommendation that you need to understand your expected access patterns from your application and let that inform the way that you're going to create your MongoDB schema. So I have a little real-world example here of a company that we worked with. And this example was a product catalog for a retailer that was selling items, right? So it's a product catalog. We have an item ID stored in the _ID field there. And they had created translations for the description of this product that they were selling in different languages. So that's what you see there in those next fields. For US English, you see they're storing the name and description. For English in Great Britain, for French, et cetera, et cetera. And this is a reasonable approach, but they were having a lot of performance issues. And what really was important was to understand the access pattern. So when they looked at their application, the lookups that were happening were a lookup by a particular ID. So that's what you see here, where we're doing a find on the catalog collection. And the first element inside those curly braces is the select predicate, if you will. Sorry, the where predicate, if you will, where we're saying where ID equals 375. But then they were saying they only wanted to see a single language at a time. And this makes sense if you think about an e-commerce website where somebody's browsing from a United States location. It didn't really matter what all those other languages are. They only wanted one translation. So there's a hidden cost with the way these documents were structured. And that is when MongoDB operates with a document, it loads that whole document into memory. And you have the choice of doing a projection when you return it to your application. So that predicate that you saw before, the second part was saying, please only return to me the US translation. So only the US translation goes back out to your application. However, down in the kernel, it had to load this whole document, search through and find the US translation, and then return that to the application. So in effect, imagine if the website was really hot right now for the United States. We really only needed those English translations, but we're using memory and I/O bandwidth to move documents in and out of your memory for all of the other translations. So the solution here was to change the document structure and have the underscore ID now represent not just the product ID, but also the translation that you want. So now instead of one document for each product with all the translations, you have one document that represents for that product the translation for Great Britain English. Another document will be created for that product for French. So this meant that we could just pull up the information that we wanted into memory and serve that back out to the application. Much, much more efficient and really a radically improved performance for this application just by making a schema change. And the lesson here is that that first schema design was not unreasonable if that's the way you expected to interact with the data, if you were always going to be wanting to look at all of your translation. That just wasn't the access pattern for this application, and we let that drive the schema structure that we want. So I already talked a little bit about sort of schema design patterns and trying to make sure that that your documents are structured in the way your application wants to use them. There's a couple of anti-patterns here. So I already mentioned importing relational schemas directly into MongoDB and having very, very large arrays. Those can have some inherent performance problems and probably means that you need to break up your document structure into multiple collections. So this is an out slide. So what I would say is that there are a lot of materials out there on very, very detailed materials on schema design. And so there's a couple of different places you can go to see those. And actually, let me just point out this blog series here. So the blog series here, the 6 rules of thumb for MongoDB modeling are definitely a great place to start that will go even deeper into this topic than I did today. So indexing. Indexing is the, probably equal with schema design in terms of the most common underlying problem that we see when we're doing performance tuning in MongoDB. Indexing is not really all that different than you see in kind of standard relational databases. So we have B-tree indexes that can be created. You can create compound indexes on multiple fields in your documents, and the indexes can be leveraged both for lookup and for sorting purposes. So, a lot of the standard performance tuning tips that you learn from Oracle or DB2 are going to apply directly to MongoDB with respect to indexing. So, a few common mistakes, obviously missing indexes, queries that you're running that either have, very selective lookup criteria or sorts that are not backed by an index. It's really easy to find these. If you have a query, you can simply append the explain method to the end of the query, and it will show you the execution path that it's using to access the data. So it will show you the indexes that it's using, or if it's not using an index, it will run something called a basic cursor, which basically means that it's looking through the entire collection. It's the equivalent of a full table scan. You also have slow queries. By default, any query that runs longer than 100 milliseconds will get written out to the MongoDB log file. That's a great place to go and look for misbehaving queries. There's also the ability to turn on profiling and have slow running queries actually written to a separate collection inside MongoDB, and then you can run some lookups against that collection. The flip side of not having enough indexes is having too many indexes. We definitely see people who get carried away and decide, well, let's go ahead and create an index on every column in this collection. Indexing is sort of a classic trade-off of, you are speeding up the lookup on the access patterns that you're indexing, but you're slowing down the writes. So every index is a separate structure that has to be maintained every time there's a write into the collection that changes those index keys. So, In practice, we often see 5 or 10 indexes on a given collection. Folks who are getting up by 20 or 30 indexes on a collection, again, might have a problem with schema design, where perhaps that collection should be broken up into separate collections. Lastly, oftentimes we'll have ad hoc queries that are running in production. So MongoDB is great and highly performant when it can run on an index that you've created, but if you have very, very large collections and there's no index backing it, you can hog up a lot of resources by running those ad hoc queries. So that's definitely something to watch out for. So this is an example of information coming from a MongoDB log file. Here you see that a query was being run against the test.docs collection. And you see the lookup predicates, the number that were returned, and the total number that were scanned in order to return that one. So that's the difference between the N to return is 1, that's the number returned, and the number of actual documents scanned, which is 80,000. So this is an example of an index that's not well, or a query that's not well indexed. And you can see that it took a total of 1.1 seconds, which is quite long. We're used to seeing sort of single millisecond response times out of MongoDB. Lastly, a little plug for a tool that's out there called mTools, which will help you take MongoDB log files and do complex filtering on them. So have a look at that GitHub repo that's listed there. If you're spending a lot of time sort of scanning log files manually using BI or some sort of text editor, you may find that mTools is a great solution to help you do that more quickly. So last few things on indexing strategies here. So obviously you need to support your queries. You'd like them to be highly selective. Just like in relational databases, if you have an index, for example, a compound index that includes field A, field B, and field C, that can be used to support lookups that include A, B, and C, or just A and B, or just A. So if you had this index, there would be no reason to have an index that was only on A, or an index that was compound on A and B, because the ABC index covers those two. Do remember that index columns can be used to support sorts. So quite a very common pattern is to see, for example, the last field in an index being a timestamp if your application is querying that collection and then asking for the query results sorted by timestamp. And if MongoDB doesn't have an index that can return the information to it in the sorted order, then it has to do its own internal sorting, which can be memory intensive. So that's definitely something you want to watch out for. Indexes can also support what are called covered queries. So this is kind of an advanced optimization technique, but the concept here is that if the index itself includes all the information being returned by the query, then the query can be satisfied directly from the index rather than following the pointer from the index entry to the underlying document. So something to bear in mind. That's also something that will show up inside your explain plan, whether or not you're using it. Lastly, kind of another fun little tip here. We often see people choose to prevent full collection scans from executing in their pre-production environment. So if you run this command that's seen down there in the bottom, that sets to no table scan, that means any query executed in that environment that is doing a full collection scan will issue a hard error. So this can be a nice way to discover if you've got bad code that hasn't been well thought out or is not properly indexed as it moves through your test and QA environments. Particularly nice because you get this hard error even if your test and QA environments don't have a lot of data and you wouldn't have noticed that it was running slowly, but it still throws this hard error. We've had this save a number of people just by adding this simple tip into their test and QA environments. So before I move to the next section, I forgot to mention, if you have questions, and I hope that you do, please type them in the chat window in the lower left-hand side there. And I do have a couple moderators who are on who will flag your chats as questions that I can answer as I go along or at the end of the presentation. And those questions will definitely help this be a more valuable webinar for you, so please don't be shy about asking them. Okay, I'm going to move pretty quickly through the monitoring section here, and it really boils down to this. Just do it now and do it in your pre-prod and stress test environments. So it's really critical as you're looking to scale your systems to understand what your underlying baseline is, and it's really critical to have a good understanding of where your bottleneck in your system may be. It's not enough just to say my query is running slow. We need to have a picture of what does my I/O consumption look like? What does my memory utilization look like? What does my CPU utilization on the machine look like? And if you haven't done that, it becomes sort of an exercise of looking for a needle in a haystack to understand why your system is running slowly. So there are a lot of different options these days for monitoring. MongoDB, the company, provides the MongoDB management service that includes monitoring and some other capabilities around backup and automation of MongoDB clusters. So this is quite easy to set up, and it gives you a really nice deep look into all of the key metrics that we've learned over the years are really critical to the health of a MongoDB cluster. So these are things like throughput, the number of operations per second that are happening, lock percentage, the various queues that MongoDB maintains for operations, how large those queues are. It also integrates with some hardware statistics through a plugin called Munin Node. So on this single pane of glass, you can see what your CPU statistics and I/O statistics are. This is available as a cloud service from MongoDB, so it's quite easy to set up and monitor and back up and automate your clusters. And this is the information if you were interested in signing up for that service. It's free for the first eight servers and quite easy to set up, and again gives you a really robust monitoring tool. I should say for those of you who are not interested in running a cloud version of this, if sort of cloud monitoring maybe violates your security policies in your organization, there is an on-premises version of this monitoring suite called Ops Manager that's available for customers of our Enterprise Edition. So just a real quick mention about the Wired Tiger storage engine. So a couple months ago, we introduced MongoDB 3.0, which really had a revolutionary change for us, which is you now have the option of one of two storage engines for storing your data behind the scenes in MongoDB. So the query language and the indexing and everything that I talked about stays the same. It's transparent to your applications, but you will now choose whether to use the memory map storage engine or the Wired Tiger storage engine. This is another topic where there's more detailed webinars on it. The high-level summary is that Wired Tiger is very, very efficient at high write workloads. So if you have a write-intensive application, particularly one that's doing a lot of inserts, you can see dramatic performance gains by moving to the Wired Tiger storage engine. So this is up to 7 to 10 times increase in throughput and 50 to 80% less storage based on some compression that's available in the Wired Tiger storage engine. So what I would say to you is if you have an existing MongoDB application and you are seeing a high lock percentage and also a high number of queues, then there's a strong chance that switching to the Wired Tiger storage engine will make a big, big impact for your overall performance. If you're starting a new application, I would probably start with Wired Tiger first, particularly if you know that you're going to have a write-intensive application. The last point I guess I would make here is that the storage engine, as I mentioned, is transparent to your application. It's 100% backwards compatible. And if you're running a MongoDB replica set, then you can do a rolling upgrade to introduce the new storage engine into your production application without taking any downtime on your system. Okay, so let's talk a little bit about vertical scaling. Everyone always wants to talk about sharding and horizontal scaling first, But vertical scaling is a perfectly legitimate way to scale your MongoDB systems. This is just simply a matter of taking the servers that you have and adding more resources to those servers, whether it's more RAM, more disk, more CPU, or maybe greater network bandwidth. You have a lot of different ways to grow your system. And this is where it's critical to have that monitoring in place, right? If you have fundamentally a problem with the amount of I/O that your system could support, basically the operations per second, adding more CPU is not going to help your system at all. So really these decisions have to be driven by what you discover in your monitoring. So in MongoDB, we have this concept of a working set, which roughly speaking equates to the data that you're actively interacting with over a given period of time. And this isn't really rocket science, but it's very helpful if that working set, the amount of active data that you have, can fit into physical memory. And so as that working set changes, you of course will have a little bit of disk I/O as different pages move into memory, and you'll have disk I/O based on the write activity that's happening. But you'll get in-memory speed if the working set can reside in memory. So one of the things that often happens is you'll find the recommendation of adding more memory to a MongoDB cluster based on that working set. And particularly with the memory map storage engine, that was very true. And there was kind of this hierarchy of needs, if you will, for a MongoDB server, with memory sort of being most often the most important resource, disk I/O capacity being the next most important resource, and then CPU being sort of the least most important resource. We have very, very large clusters running the memory map storage engine where the CPU utilization is in the 10 or 20% range. That equation has changed a little bit with Wired Tiger. Because Wired Tiger has compression involved, which is a little more CPU intensive, we're starting to see a greater consumption of CPU cycles on MongoDB servers, and again, less I/O, in part, again, because of that compression that's happening. So a quick real-world example of doing vertical scaling. So we had a company that basically had a generic system for capturing changes in business entities. So these are things like a sales order status changed or an inventory count changed. And it was just sort of a big data dumping ground for all of these events, with the concept that they would then do some deep analytics on those events. And there was really a high write activity that was happening. And also the updates that were happening into the system were fully random. So as the data set got larger and larger, even the very old business entities could still get changed, in part based on these 100% updates that they were doing, where they were enriching them with new information that they had decided they wanted to track. And so they had started with a sharded cluster that had 4 shards that was backed by spinning disk. And pretty quickly, based on the need to push these writes through quickly, they started to grow to many, many shards. So it went from 4 shards all the way up to 16 and more shards backed by these spinning disks. And this worked fine, but it wasn't sort of cost effective for them. The value of the system wasn't really matching the investment they were having to make. And so they called us in to do some consulting, and we actually recommended that they move away from spinning disks and move to SSDs. And this allowed them to scale all the way back to that 4-shard system, still meet their throughput requirements because they now have the faster disk backing them. And this is a common solution, moving from spinning disk to SSD, when you have that fully random access into a moderately sized data set. So if you think of the memory that's available on your server as being a caching layer, which it really is, we're going to get our memory speed access when we move the data into there, then you can sort of understand that caching layers really only work when you do have non-random access into the data, when you can keep hot data resident and there's colder data that's less likely to be accessed out on your slower rotational disk. In this case, as I mentioned, it was really fully random access in there. So we were still driving a lot of I/O, and we still would have been driving a lot of I/O if we had added memory. The real trick was to make the underlying I/O itself faster by moving to SSDs. And so if you have a moderately sized data set with fully random access into it, often SSDs will be the right solution. I say moderately sized because for the very large data sets, oftentimes you can end up with SSDs being prohibitively expensive, although I will say that's changing quite a bit. And we are seeing SSDs as more of a standard server architecture at this point. So I already mentioned a few of these things. Before you add hardware, make sure you understand where your bottleneck is. Have a look at schema design and indexing first. It's probably up by 95% of the problems that people come to us with are solved by schema design and indexing. There's a set of best practices for tuning things like the operating system and the I/O subsystem. Make sure that you're following those recommendations. They're basically all brought together in a page called production notes inside the MongoDB documentation. So if you just search on MongoDB production notes, you'll get right to that page. My last little warning here is to have a look at the startup warnings that appear in your MongoDB log files, because we do check many of those recommendations in production notes, and we'll flag them as warnings about those best practices. So let me have a quick look here and see if there's questions I can answer at this point. Okay, so there's a question here. How can we avoid creating non-ideal anti-patterns when migrating a large-scale application from a relational system to a document format database like MongoDB? There's not sort of a straightforward answer to that, other than making sure that your teams that are doing the migrations are well educated on sort of document modeling and a lot of the things that I talked about at the very beginning of this presentation. It can be a bit of a change for those relational folks to make the jump to a document database, and they need to be educated on the benefits of kind of following a document model. The last thing I would say is, if you're separated from your development team and they've done the port and you're an operations team and now you're trying to look at the application they've written against MongoDB and understand if it's well written, look for those rich document structures, look for proper use of arrays. You see a lot of repetitive queries. What will happen if you follow the standard relational schema, right? You could have that sales order. You could have one collection called sales order headers, okay? And then you could have another collection called sales order lines. Sales order lines could include the header ID on it, right? And so you can break those up into separate collections. It just becomes the application's responsibility to do that join. So if you see a pattern where somebody's looking up the header ID, and then right after that they're issuing a cursor looking for all of the lines that relate to that header ID, if you start to see that pattern in the applications that you guys are supporting, that might be an indication that they're not sort of following best practices for document design. There's also a question here. Is there any process in Wild Tiger running in background and compressing existing data without our notice? So Wired Tiger gets enabled for each replica set member, which is basically the MongoDB process that is running on a separate node. So if you wanted to move to Wired Tiger, the process you would follow is to take one of your existing secondaries down, wipe out its data structure, and then start that secondary back up with configuration options saying, please use the Wired Tiger storage engine, and saying which compression algorithm to use. Once that member rejoins the replica set, he'll do what's called an initial sync. So he'll ask the other members of the replica set for copies of all the documents, and he'll take those copies and he'll write them into his storage engine, now following the Wired Tiger storage format and doing that compression. So while he's doing that, he's not sort of a fully functioning member of the replica set. So your application, if it was doing secondary reads, would not be able to talk to that node. Once he's done all of his copied all of the documents, and looked at the op log to take the most recent changes to the database, then he would fully join and you could use him as a full member of the replica. Okay, let me move to the next section here, which is on horizontal scaling. So, this is our method for doing partitioning, and we call it sharding. And this is another one like the WiredTiger storage engine that is fully transparent to the application. So whereas before your application and the MongoDB driver would have been talking directly to a replica set, now it's connecting to a query router. And this is, if you're familiar with the architecture, it's the MongoS process that could either be running directly on your application server or somewhere down in the database tier. And that query router then has a look at the operation that you're doing, and it decides which replica set member or members need to be part of that operation. So the way this happens is for individual collections, you decide that you want to do sharding on that collection. And the example I like to use is imagine that you had a user's collection that was storing maybe user profile information or maybe even authentication information. And those users ran from somebody who started with AA to somebody who ended with VZ. What we'll do when you shard that collection is you'll say, please shard by username. MongoDB behind the scenes will go and have a look at that collection and break it up into different ranges of those usernames. So there might be a chunk that is from user AA to user BC, and then the next chunk would be from user BC to user DF. We'll break those up into individual 64 megabyte chunks and then scatter those chunks across all of the replica members that you have added to your, or all of the shards that you've added to your replica set. You see here we have shard 1, shard 2, shard 3, and all the way up to shard n. Individual chunks of those usernames would be located on each one of those shards. And then as you did a lookup on a username, the query router decides, oh, I know that because this username is in this particular range, I need to go and talk to shard 1 to retrieve that information. Or I know I need to go and talk to shard 3 because it's a different username. So there's a fundamental rule with shard keys, a couple fundamental rules that you need to follow. So the first one is you need to pick a shard key that has sufficient cardinality. So if you were to shard on a field that was, for example, a Boolean or a gender field, male or female, we can only break those into 2 separate buckets. So we could only ever have 2 shards in that system. That's a pretty straightforward rule, and it's not often, not often violated when people choose to do their sharding of their systems. The next 2 rules are the ones that we see people trip across. So when you shard a collection, you want to choose a shard key such that the incoming writes to the system, the inserts to the system, or updates are evenly spread across the shards that you have created. So where this becomes a problem is if you choose a shard key that has a monotonically increasing value. So if you were to shard just on timestamp of when this event is coming into the system, that would mean that there's always one shard that is from a pretty recent time in history to basically positive infinity. And all of the writes would be coming in onto that chunk. So this gives you what you would call a hot shard. So you're not scaling your write throughput if the vast majority of your writes are always landing on one particular shard. And it's even a little bit worse than that, because if you have a hot shard, that shard's going to fill up over time. And MongoDB will detect that and will actually notice that a chunk is getting too large and will split it. Once we have too many chunks on that shard, we will, behind the scenes, pick up the rows from one chunk and migrate them to another shard. So we do that balancing automatically, and it's transparent to the application, and you still have full read-write access to your data while that happens. But it does represent extra work on the system. We're having to physically copy the data to another node, the data to another node, and delete those documents on the existing node. So if you choose a bad shard key and you get this hot hot shard, you'll have a lot of underlying activity that's happening on the system that you'd like to avoid. The third rule of thumb here is choosing a shard key where you get targeted reads. So if you remember the user ID example that I had, lookups that are happening on that user ID, we can route to an individual shard because that user ID is part of the shard key. But if I were doing a lookup on email ID or age or some other thing in that user collection, then MongoOS would have to send that query to all of the shards in the system, get an answer from every single shard, and then combine those results. This is another one that works absolutely fine, and MongoDB will return the correct results, and it actually executes pretty quickly on those individual shards if you have the proper indexes on those individual shards. But it, again, represents some extra work that's having to be done, and particularly in very large systems that have, hundreds of shards, you will be beholden to the slowest shard before you can get an answer back. And basically, it won't linearly scale queries that don't include the shard key. So if you follow those two rules around distributed writes and targeted reads, then you can get that linear scalability that you want. So again, this is just an example of watching out for ascending shard keys, those monotonically increasing shard keys that could give you a hot shard. I mentioned timestamps. The _ID field is another one that people will sometimes choose to shard on and is oftentimes not a good choice. By default, if you have not supplied your own value for that _ID field, we generate a unique key. That unique key happens to be monotonically increasing. So if you're using that default value for the _ID field, it's usually not a good candidate for sharding. Or I should say, that _ID field is not a good candidate to be the shard key on that collection. There should be some other key or set of keys that would be a better choice for you. Okay, real quickly, scaling your operations team. We've seen a lot of people, have issues once they start to try and manage and operate a 5-shard system or a 25-shard system or a 120-shard system. This is where tooling becomes very important, and the MongoDB management service that I already mentioned, can be a big part of helping you manage those very, very large clusters. Again, in this case, things that would have taken literally hundreds of steps, either through the command line interface or through scripts that you have created, can now be done through our UI or through API calls to the MMS or Ops Manager if you're running the on-premises version. Again, this screenshot is an example of creating a new cluster, using servers that you've identified, setting the version that you want, setting configuration options like using WireTiger for all of the nodes in this particular cluster. Again, we're trying to make it so that you can manage things at the cluster level instead of having to perform individual operations on each node in that cluster. So again, deploying clusters, upgrading or downgrading the MongoDB software, adding or removing shards, resizing the op log, creating users and roles. We also have a tight integration with Amazon Web Services such that we can create and deploy machines for you in Amazon as well. So before I move on to the last slide, let me see if there's a couple more questions here that I can answer. So there is a question here. What is the speed at which data is moved from one shard to another? And what happens if data that has not been fully moved to a new shard yet? Will it be retrieved from the old location? So the first part of that question, the speed is just wholly dependent on the infrastructure that you're running on. So it will be governed by the speed of the server both the server that you're pulling the data from and the server that you're writing the data to, and that may be governed by, again, CPU or I/O bandwidth. Network obviously has an impact here as well. So, you want to do sizing of your system to make sure that you have properly sized clusters to support this kind of activity of the migration of the chunks. If, for example, a chunk is migrating and something goes wrong and the migration can't complete, the old location is where the queries will be resolved from. Behind the scenes, what's really happening is as the donor shard is pushing the documents over to the recipient shard, he does that, and then there's a cleanup step where the recipient shard goes back and says, okay, have there been any changes to these documents since I started the migration process? And so he can pull those changes over. And he does a couple passes at that to know that the documents that he has are 100% up to date. Then he makes sort of the atomic switch to say, okay, now I am the source of the truth for these documents. So until he gets to the point where he does that atomic change of becoming the true source for those documents, until that happens, the old shard is really the source for those documents. So I have a question here if there's a solution for on-site monitoring like HP OpenView or application lifecycle monitoring. So there's two answers to that. One is there is an on-premises version of the MMS service I was talking about. That's called Ops Manager, and it's something that MongoDB as a company sells as part of our enterprise subscription to MongoDB. That also includes the ability to use APIs from that Ops Manager software to push information into other monitoring solutions, whether it's OpenView or Nagios or some of the other ones that are out there. So we realize that monitoring is more than just MongoDB, and that we want to integrate into your standards for your data centers. We do see a lot of people going with sort of a hybrid approach where they will push some of the key metrics into their higher level monitoring solutions. But for deep dives on performance troubleshooting of MongoDB, they'll often still have Ops Manager running so that they can get that deep, comprehensive picture of all the stats that are happening inside MongoDB. So I do have another question here of, is MongoDB using vertical partitioning too? I'm going to assume that sort of vertical partitioning means within a given collection and running on a single instance, partitioning that collection so that you could do adds and drops of whole partitions of data, but do queries of kind of that aggregated all those partitions that you've included. So I'm familiar with the way partitioning works in Oracle, for example. And the short answer to that is no. We don't have a vertical partitioning capability inside MongoDB. If I didn't answer that question correctly, if you wanted to ask a clarifying question, go ahead and type it in the chat box. Okay, we're pretty much out of time. If there's one or two questions I didn't get to, I'll see if I can answer those offline for you. I wanted to close just by mentioning that we have many customers who are running very large MongoDB implementations. So whether it's by number of servers in the cluster or number of operations per second or the size of the data that's being held inside these MongoDB clusters, we have a lot of folks running at very large scale. And in particular, what's very interesting is many of these, well, all those on this slide are doing that with the memory map storage engine. So now with WiredTiger being introduced, I think there's a whole new level of scale, in particular for write-intensive applications, that you'll see MongoDB getting used for. And it's a pretty exciting time for us. I hope that this webinar was helpful. Again, it's a very high-level webinar. If you want to dive deeper on things like sharding or schema design, have a look in the webinar section at mongodb.com. There's a lot of great information you can get to. Our documentation is really top-notch as well, so you'll find not just sort of a technical description, but you'll find tutorials and how-tos directly in the documentation. Lastly, there is a survey that will appear in your window at the end of this webinar. Please fill that out if you can. It really helps us tune our future webinars to make sure that we're providing information that's valuable. Thank you very much, and have a good day.